Welcome back to the Deep Dive. Today, for all you number theory students out there, we're digging into the OEIS, the Online Encyclopedia of Integer Sequences. We're focusing on one sequence in particular, A00282, and it's really quite surprising linked to something called finite automata. Our goal here is pretty straightforward. Quickly pull out the key insights about the sequence and why it matters. Okay, so let's unpack this. A00282, you look it up, it's just a string of numbers, 370, 3783. But apparently it holds a kind of secret about computational structures.
It does, yes.
Yeah.
What's fascinating here is how these models of computation, finite automata, which are conceptually quite simple, really lead to these incredibly large, very specific counts. They're like the basic building blocks for processes that take input, change state, and produce output. Think simple machines.
Right. So let's get specific. The OEIS definition for A00282 says it's the number of inequivalent N-state two-input, two-output connected automata with respect to an input permutation. That's a lot. Yeah. Could you break that down a bit?
Right.
What does N-state or two-input, two-output mean here? And maybe especially connected and inequivalent.
Certainly. So N-state just means the machine has distinct internal configurations it can be in. Simple enough. Two input, two output means it has, well, two channels for receiving information and two for sending results. Pretty standard setup for comparison. Now, connected automata, that's important. It means all the states are reachable from one another. There aren't any sort of isolated parts just floating there unused.
Oh, okay. So the whole thing works together. Makes sense.
Exactly. And inequivalent is maybe the most crucial part for counting. It means we're only counting genuinely different structures. We ignore machines that are basically the same but just have different labels on their states or inputs. It's about classifying the fundamental forms of these computational units.
That distinction, inequivalent, sounds subtle but really important. Does it drastically change the numbers compared to counting every possible labeling?
Oh, absolutely. It's fundamental for getting a meaningful count of distinct structures. Without it, the numbers would be far, far larger and wouldn't tell us much about the variety of unique machine types.
And that variety grows fast. You mentioned the first few terms earlier, 3, then 70, then it jumps to 3783. Wow. I mean, look at how quickly those numbers explode. What does that tell us?
It tells us that the combinatorial possibilities, the number of ways to wire these states together, even with just two inputs and outputs, just skyrockets as you add more states. And, this isn't some new curiosity. People have been counting these for a while.
Right, the sequence goes way back.
It does. It's in Sloan's original 1973 handbook and the 1995 encyclopedia. A really key source mentioned in the OEIS entry itself is Michael Harrison's 1965 paper, A Census of Finite Automata.
1965.
Yeah.
So why were mathematicians back then so interested in counting these specific structures? And why does it still resonate today?
Well, it gets to the heart of understanding the limits and possibilities of computation, even simple computation. Harrison's work was foundational.
And that 65 paper, the OEIS entry points to specific theorems from it, right? Theorem 6.2 and 7.2. It sounds like there's a relationship there.
Yes, precisely. Harrison provided the mathematical tools. Theorem 6.2 essentially helps count all such automata of a given size, including ones that might be disconnected.
Okay, so that gives a broader count first.
Exactly. Then Theorem 7.2, often used with something called the inverse Wehler transform, which is a technique from combinatorics, lets you sort of filter that count. It allows you to precisely isolate and count only the connected automata, the ones that are, irreducible, non-decomposable structures.
The inverse Wehler transform. So that's the mathematical link connecting the count of all automata to the count of just the connected ones.
That's the idea. It's a way these abstract mathematical operations help us zero in on very specific, meaningful structural properties within a larger set. Quite elegant, really.
So bringing this back to you, the listener, what's the takeaway here? I mean, it shows how incredibly precise mathematics can be, right? For sorting and understanding complex systems. Not just theoretical computation, maybe, but potentially things like algorithm design or even engineering.
I think so. It demonstrates this deep structure. A00022 gives us a concrete number for a specific, fundamental type of computational building block. It reveals just how intricate this world of counting combinations can get and how fast complexity grows. And think about it. Every time you use a vending machine or a traffic light system or even interact with software, you're touching systems that operate on principles related to automata. This deep dive into A00282, it's really just one window into the rigorous mathematical frameworks that underpin our understanding of all these automated systems.
A great point. It makes you wonder, What other complex systems, maybe even ones we don't typically think of as computational, could be described or counted using integer sequences like A00282? And how might looking at them through that mathematical lens give us completely new insights? Something to think about until next time.